Good morning, everyone. Well, I was presented already. I come from the Department of Mechanical Aerospace and Civil Engineering in the University of Manchester, and I was asked to talk about models for brittle fracture. But it's actually going to be about local approaches to cleavage as they are known, because I'm not going to touch upon quasi-brittle materials, cement-based materials. It's going to be about steels again. And the outline of my talk is I just want to start with motivation for these local approaches and some experimental observations that back up their development. Then I'm going to move to the mathematical or statistical basis for local approaches. It's more statistical, it's less mathematical. In fact, I have a lot less mathematics than the previous talk. And then I'm going to present some practical applications of these local approaches. And my emphasis actually during the entire talk is that there are challenges with these local approaches that need to be addressed. And then I'm going to give these challenges as opportunities for you when you move on with your careers. Maybe you can improve a lot on these local approaches, and hopefully I can have some questions. And of course, not mandatory applause. So let me start with the motivation. It comes from the need to do integrity assessment of our engineering structures. And here I give an example of the basic procedure for integrity assessment in the nuclear sector in the UK. But the philosophy that is here is actually used in many countries. So this philosophy is based on a failure assessment diagram. And in order to assess the integrity, one needs to calculate two parameters. One is on the x-axis is the so-called proximity to plastic collapse, where you need to calculate a plastic collapse load or reference stress, which can come from finite element analysis or compendia for a particular defect. And also you need the yield stress, which needs to come from testing. And on the y-axis, you have the parameter is called proximity to fracture, where you need to calculate the stress intensity factor for your cracked geometry. And then you need to have the fracture toughness or the material fracture toughness in the denominator. And when you calculate these two parameters, do you see my mouse actually? Probably not.
Yes.
Yeah. So you're going to have an assessment point, which may be inside here, which is the safe region, or outside, which is the potentially unsafe region. So this is the basic for integrity assessment that the nuclear business uses. However, well, typically the determination of the yield stress is not so difficult. I mean, the variability that you're going to get in yield stress is not large. So you can have a pretty good estimation from simple tensile tests for your yield stress. But the problem is the material fracture toughness, which usually we measure with some standard specimens like the 3-point bend deeply cracked specimen here. And now, if we want to use what is measured here, we must assume that there is a mechanical similitude between the geometry and loads in our test and the crack in our real geometry, in our real structure. And the problem with this is, well, we can continue like that, but there are several problems. One of them is that the similitude may break down. And the other one that we have is that there are aging and temperature effects that we need to capture. And so when I say similitude breakdown, this may happen because of constraint effects, size effects, load effects. There is a difference between the geometry that we test and the crack in our real structure. This is, I think, this is a detail of the nuclear power plant. And more importantly, For the materials that I'm talking about, which are different from the materials that Jeremy spoke about austenitic steels, and the brittle or cleavage fracture is not typical for austenitic steels. It's typical for ferritic steels and other body center cubic metals. We have the following thing. We have temperature effects. So our stress, either yield stressor or ultimate tensile strength, are decreasing with temperature, but our fracture toughness is increasing with temperature. So this here, the black curve is showing the temperature dependence of fracture toughness, something that is not, again, it's not typical for austenitic steels. And the problem with constraint, for example, is that the fracture toughness that you measure and the dependence of fracture toughness on temperature is shifted to the left from the high constraint fracture toughness that you would measure with specimens like this one or this one. While some aging factors, like, for example, radiation-induced damage in the material, may shift this curve to the right, as the red curve shows. So that, I'm sorry, this seems to be, oh, well, this is the average fracture toughness. That's the meaning of K 0.5. So on the top of that, the fact that we have temperature dependence and aging dependence and constraint dependence, we have an additional problem with cleavage fracture, which is stochasticity of the phenomenon. If you measure the fracture toughness at different temperatures with different specimens, for example, these are compact tension specimens with crack front length 25, which is the standard 50, 100, and 200, and you measure it at different temperatures, you're going to have a big scatter in the results. So there is a scatter in the results here with compact tension specimens, but then if you measure with a different crack depths, which you can do with a 3-point bent or SEM-B specimen, you can see that there is a difference in the probability of fracture as a function of the applied J integral. And so the conclusion from this is that we have a large scatter, and this suggests that there is a strong microstructure and load controlled phenomenon here. And this scatter means that the toughness values depend on temperature and on the crack tip constraint as a minimum. So what are our assessment options if we know this? We can continue doing our global approaches, and I assume that everyone is familiar with the KC and JC, the critical stress intensity factor or critical J integral, but they can be based also on critical crack tip opening displacement. These are simple to apply, the global approaches, but you cannot predict the temperature effects so easily without testing actually at every temperature. You cannot predict easily constraint effects, although there are some two-parameter approaches you may be familiar with, like JQ approaches, and you cannot address the stochasticity, the stochasticity of the probabilistic nature of this process. And so people started thinking about these local approaches or local models for fracture, which are supposed to couple the knowledge of micromechanisms with mechanical analysis. However, our local approaches for cleavage or for brittle fracture are not encaptured in constitutive equations as the local approaches for ductile fracture. So in local approaches for cleavage fracture, there is no change of material properties as the load goes. It's a probabilistic simulation, as you'll see in a second. So we we have the development of these local approaches that you'll see, and the advantage is that we can model the physics of cleavage at macrostructural level. We are not there yet with everything that we know or the things that we don't know, but in principle, they should be able to model the physics of cleavage. They are currently capturing the stochastic nature of cleavage. And our problems are that we have limited knowledge of all the mechanisms that I'm going to show in a couple of slides. From one side, we have limited knowledge. From other sides, the engineering profession asks us to make the models as simple as possible. And so we have some problem here. So cleavage fracture, what is known from probably the mid-60s and then 70s, is something that originates at ruptured second phase particles. And these second phase particles, which may be carbides or sulfides, they rupture because they are some sort of a ceramic material, so they are almost very brittle. And then when the plasticity develops in the surrounding matrix, the metal matrix, the particle needs to take the entire strain, and it develops high stresses and it ruptures. So it's called plastic overload. And the stochasticity comes from the fact that these particles are randomly distributed in the material. So if you have two specimens and you load them to certain J, one of them may fracture, may cleave, because it just found a larger particle in the region of high stresses than the other specimen. So you probably need to load the other specimen more. So this stochastic or random spatial distribution of particles is the reason for the measured scatter in fracture toughness. And a minimum requirement for local approaches would be to account for these first observations. Now, what is the fate of particles, one may ask? A particle may, for example, detach from the matrix and form void immediately. And then we are going into the realm of what Jeremy was talking. If this is the case, this void will start growing, and then we have a situation that is not exactly cleavage fracture. If the particle ruptures and forms a microcrack, again, we have a situation that this microcrack may blunt because the local stresses are favorable of actually blunting it rather than keeping it sharp. And so it forms a void again, and we go back to the situation that we have sort of a ductile fracture, like the one that is shown here, so with typical dimples. And then if the local conditions are such that the microcrack may remain sharp, I would call it an eligible for fracture, for cleavage microcrack. But whether it propagates, it depends on the stresses on this. So you may have a particle that ruptured, formed a sharp microcrack, but the local stress is not enough to cleave the entire material. And so there is an additional condition here that the stress on the eligible microcrack should be larger than some critical value. Right. So how do we represent this mathematically? Now, people think, I borrowed this picture from a friend of mine. People think about this as a random distribution of microcracks of different sizes in a region that is ahead of a macroscopic crack. And this is what is called fracture process zone. And the fracture is controlled by the critical microcrack. So these are the things that we know from experiments before development of the local approaches. One thing that is misleading in this figure is that these microcracks are sort of homogeneously distributed, but that's not exactly the case, because ahead of a macroscopic crack, we have a gradient of stresses and strains. So actually, the distribution of these microcracks may not be homogeneous. And because of that, the cleavage fracture can be modeled actually as an inhomogeneous spatial Poisson point process, which some may have seen as weakest link process. And the major assumption behind this process are that the failures that may happen are independent when the volumes in which they happen are non-overlapping. So we have independent failures, which allows actually to formulate it as a weakest link. The second assumption is that the probability of failure in an infinitesimal volume is proportional to the volume. And the probability of more than one failure in an infinitesimal volume is 0. So these are the three assumptions that lead actually to the equations. I must admit, I don't know whether the original model, which you may have heard is called the Berryman model, has been based exactly on this way of thinking, but it leads to the same result. So, if you open the books on statistics and look for the spatial Poisson process or inhomogeneous spatial Poisson point process, you'll find out several definitions here. It starts with an intensity function, which actually describes the probability of finding a point within an infinitesimal volume delta V located at point X, sorry. And this is what makes the process inhomogeneous. I mean, this intensity may be different, may change from point to point, from location to location. And then we have big lambda of V, which is the intensity measure, which is the expected number of points in a volume V, which is just an integral of the intensity function. And then the probability of finding a point in a volume V is just 1 minus e to the power of minus lambda of V. So this is exactly the mathematical basis for the Berryman model you will see in a second. But on the top of that, in the Poisson point process theory, one can introduce something that's called a thinning function, which is just saying, I have some points that I want to throw away of my original process, and I want to keep the rest. So this thinning function is actually saying I'm keeping some points of the original point process, and then this leads to a new Poisson point process that is formed by the kept points, which is just simply the thinning function times the intensity function of the original process. Now, how is this specialized for cleavage? Now, if you think of our succession of events, we have a second phase particle which breaks, and then we have a broken particle which may propagate into the surrounding matrix for a while. So this is a sharp microcrack eligible for cleavage, which I'll denote as EMC, eligible microcracks. And then if this microcrack has a size that is larger than some critical value, I have an intensity of cleavage initiators. And so what in the Poisson point process, what is a point there is here actually a feature that is larger than some critical size. That's a point in our case. It can be, you can think of it as a particle, and then for particles we do have measurable sizes and measurable density. You can think of it as an eligible microcrack. We don't know much about those. And this figure here, the top figure shows a typical distribution of particle sizes, and the bottom figure shows a distribution, the assumed distribution for eligible microcracks or cleavage initiators. And the thing is that the Berryman approach and many other approaches assume that the size distribution of these features, whether it is particles or eligible microcracks, is a power law. Why is this? Because it has a very simple integral. So the size distribution of features gives an intensity function that is the integral from a critical size and a particular location of the size distribution of these features, and it gives again a power law. So the intensity function for whether you're thinking about particles or eligible microcracks is this power law here at the bottom of the slide. Now, what can we say now about the intensity of cleavage, about the intensities of different things? For a particle size distribution, we can have the intensity immediately because we can measure the particle sizes and you can measure their densities. The thing is that if we measure this, we can go here and we can actually fit a power law to the tail of this distribution, and we can represent it as a power law. However, for the microcrack intensity, we don't know much. So it may have a different shape from the particle size distribution, which is actually used quite a lot. As you will see, actually all our models are based on a different microcrack intensity because we fit to experimental data. But I find it very difficult to justify. I just can't see to this date why the microcrack intensity would be different from the particle size distribution. It can have the same shape, of course, which I think is more logical, but it's not fitting the data. And then one can think in this case of the eligible microcracks as a thin subset of all particles or all microcracks at a particular location with some thinning function theta of x, which keeps only the eligible microcracks, not the ones that are going to blunt. Now, in that case, the cleavage initiator intensity takes this form that is on the bottom of the slide. So you have a thinning function and you have the integral of the either particle or microcrack size distribution. And so how is this implemented? So the original model, I mean, this is a whole class of models that is called Weibul stress models, but the original model assumed that the critical microcrack is given by the Griffith criterion, which is shown with the first equation. So that, of course, critical microcrack depends on the location because the stress changes with location to location. Then the intensity of the cleavage initiators becomes this value here. Lambda theta is the thinning function times sigma 1 over sigma u to beta minus 2. You can do the maths, actually. There is some homework for you, where sigma u is a parameter that depends on the material properties as well as one of the parameters of the microcrack of particle size distribution. And if you plug everything into the statistical basis, you're going to end up with a probability of cleavage that is given by this equation, 1 minus the exponent of sigma w over sigma u to a power of m, where m is actually now 2 beta minus 2. And the sigma w is something that in the local approaches is called the crack driving force now. So our crack driving force is not the J integral, it is the Weibul stress, which is given by this integral here. So the thinning function, sigma 1 to the power of m, integral, and the entire story to the power of 1 over m. And I just want to mention here that actually the intensity measure in this case is sigma w over sigma u to the power of m. So this is the correspondence to the mathematical part. And actually this intensity measure is giving you the number of cleavage initiators in the volume V. That is what the mathematics tells you. So what are the thinning options that have been proposed so far? The original Berryman model, the thinning function was just, it wasn't formulated this way, but it was just the Heaviside function of epsilon p, which means when epsilon p is larger than 0, it's equal to 1, the thinning function is 1. When epsilon p is 0, when there is no plastic strain, so when we are outside of the plastic zone, the thinning function is 0. And so that reflects the observations that plastic strains are required to generate microcracks. But it also takes all the entire plastic region. Whenever there is a plasticity, there is a contribution to the probability of fracture, apparently, because the thinning function is just 1. There was the first modification that is already in the original Berryman paper. It was a thinning function that is epsilon p to some power alpha. And it's been used by many people after that in different situations. You can see in the literature. That reflects observations, experimental observations, that microcrack density is increasing with plastic strain, but there is a conceptual problem, a serious one in my opinion, that it doesn't fit the mathematics. I mean, you cannot have a thinning function that can become larger than 1. And in this case, it can, because epsilon p can be quite large. There is nothing that can limit the thinning function in this case. And another one that was proposed later was 1 minus the e to the power of minus lambda epsilon p. And so that is an eligible thinning function because it does give you, it is actually limited between 0 and 1. And here you have a parameter, fitting parameter that's lambda. In the first case, you have a parameter that is alpha here. So what has been done with this? In the early developments, when the model was proposed, and several years later, people defined they thought a rigorous process to calibrate the parameters of the model, which are essentially the shape of the model, which is m, the shape parameter, and the scale parameter, which is sigma u. And so they said, okay, perform tests with one geometry at one temperature, do the corresponding finite element analysis, use this thinning function, which was the original Berryman model, and you start iterating to find the m and sigma u that minimize the difference between the data and your finite element simulations. This didn't work well because people soon after that found out that there are infinitely many pairs of m and sigma u that can provide equally good fits. This figure here shows a calibration for a steel at tested particular temperatures, which are these black dots. The blue curve is the maximum likelihood fit to the data directly, and the red curve is simulation, which means it has been iterated to find a particular m and particular sigma u. Now, this part that there are infinitely many pairs led to further developments that suggested that one needs actually to do two tests with substantially different constraint conditions. For example, in this figure, we have tests with 3-point bend specimens with crack depth over width 0.4 and 0.05, and then use one of the methods, use one of the thinning functions, let's say this one, and iterate again to find m and sigma u that predict at the same time the measured fracture toughness. This is actually the so-called characteristic fracture toughness, the fracture toughness at a particular percentile 63.2, that predict the measured fracture toughness for both sets of specimens. So that is the next step that people did, and it has been used quite widely. And further, further calibration was proposed that is based on the use of a thinning function, the third thinning function that I showed a couple of slides back, which is used the exponential function of the plastic strain. So, and the approach here is to first actually calibrate with the standard Berryman model, with the first thinning function, and then start iterating to find the best fit by calibrating the parameter lambda. And this is shown on the right figure, which is a bit tricky to understand, but these are curves which provide pairs of J values which produce the same Weibul stress in the two models. So, for example, this point is a point where the Weibul stress in the model with deep crack, which is this one, and the model with deep crack, which is this one, and the model with the shallow crack, which is this one, have the same Weibul stress. And so you can build such curves for Weibul stresses using this function, using the function theta, and find out which of these curves, for which value of lambda, we have the best fit to the experimental data. And so this was the experimental data point, the characteristic toughness for 0.4, something like 40 joule per square meter, and this is something like 78 for the shallow crack. And we had some successes with this calibration. We managed to do to show that this type of calibration is possible. With this type of calibration, we can find the changes of fracture toughness due to constraint effects and also load history effects, particularly prior plastification of the material. However, exactly as in previous cases, the Weibul shape parameter is not, it's far away from the measured shape of the particle size distribution, which again suggests that there is something that we actually don't know. I mean, all these things, all these differences between the shape parameter of the particles, which is measurable, and the shape parameter that you find by fitting fracture toughness data, suggests that we don't know what is the conversion between particles and microcracks. Why is the microcrack shape parameter actually changing? And the other problem is that this is not transferable across different temperatures. And so for temperatures, we had a different sort of proposal. This is the ductile-to-brittle transition example that I wanted to show. If you remember on one of the first slides, I showed this temperature dependence of the fracture toughness of these particular materials, of ferritic steels, and that temperature dependence is called a ductile-to-brittle transition. So here we proposed a very particular thinning function, which has a temperature dependent, where the parameter lambda actually is temperature dependent, and epsilon p stays. So we use the same thinning function as before, but we make the lambda parameter temperature dependent. And we managed to find out a particularly good fit. But, and of course, this is in line with our previous developments, but it is essentially fit to what we have as experimental data, which is shown on this graph. It suggests that there is some sort of, that one can look for some sort of thermodynamic explanation, because there is a strong exponential effect and it resembles the Arrhenius relation. But we were not able actually at that point to find out an explanation. So this was rather successful to predict changes in fracture toughness. So if one measures the fracture toughness at a particular temperature, with this fit for this particular material, one can predict the fracture toughness at a lower temperature and the fracture toughness at higher temperatures in the ductile-to-brittle transition regime quite well. And also the predictions of the probability of failure as a function of the J integral. Again, I need to point out that while the predictions were good, you actually need the data for this particular material at several points in the ductile-to-brittle transition regime in order to build such a heuristic, I would call it, expression for the temperature dependence. And it seems to be not universal. So the thinning function needs to change with the geometry. And if you need to change the material, you need to do again the same tests. So so I'm coming to my summary and opportunities. In summary, for the local approaches, for constraint effects provide pretty reasonable predictions by cross-calibration. But this works only for one temperature. And the predictions and the fitting that you did there with cross-calibration for your shape parameter and for your scale parameter are not going to work for other temperatures. There is no clear reasons for why M should be changing. The argument that I hear is not convincing. So what I'm trying to say is that if one wants to calibrate only with with one particular constraint, one is going to get some M parameter and some sigma U. If one wants to calibrate with a different constraint condition, it's going to get a different M and different sigma U. And when one makes a cross calibration, one gets some M in between. Why? What is the reason to have different shape of the size distribution of microcracks is not clear. And so in this case, at least we need two sets of data there is no link to the underlying processes at present. It's just a calibration with the macroscopic data. And for the temperature effects, which are also important for structure integrity assessment, what I can say at the moment is that the mechanical fields that we obtain by finite element analysis seem to be insufficient to formulate a thinning function that delivers the observed behavior, the observed temperature variation for all cases. You can do a particular thinning function, but that's going to be for a particular material and for a particular constraint condition. So from one side, you can probably fix the constraint effect at a particular temperature. From another side, you probably can fix the temperature effects with a particular constraint, but we don't have a method that can do both at the same time. And so my conclusion here is that we started with these local approaches to incorporate some knowledge of the micromechanisms, but I think that we need further understanding and incorporation of micromechanisms that are beyond simple particle continuum fields. At the moment, we use continuum fields, we use finite element analysis with our deformation properties only. So this is very different again from the ductile fracture that Jeremy spoke about, where the material properties change because of void growth and coalescence. Here, the material's properties do not change during the simulation. And that means that the damage that is created by microcracks formation is not taken into account. The material properties are just the deformation properties that you put in your model. And possibly we need to go beyond this simple particle continuum fields interactions. And where I think the sources of limited predictability are, and the opportunities for you, the biggest source for me is that we have insufficient knowledge of micromechanisms. We need more experimental data on how mechanical fields control the conversions between particle to microcrack, to eligible microcrack, and to initiator. Let's leave the last two. They are the same thing. It's captured by the critical microcrack size. And so we need here further research to construct a physically based thinning function. If we continue with the Poisson point process or the weakest link. But there might be, my second point here would be, there might be that the statistics that we use to build this local approach is not adequate, for example, for all temperatures, because this may not describe the physics correctly, because it does not take into account interactions between microcracks. You remember that one of the basic assumptions for the Poisson point process is that the events that happen in separate volumes are absolutely independent. it's quite possible that the number of cleavage initiators that should be taken into account is less than the number of initiators that are taken into account by the current model, particularly when you increase the plastic strain or temperature, which is when you increase the temperature, you also increase the amount of plastic strain because the yield stress is reduced. And that's why I think the further research is required here to understand the microcharacter interactions and potential change of the statistics to something else. That in the limit of very low temperatures and the very low plastic strains is actually becoming Poisson point process, because the weakest link is really working well for temperatures that are below certain temperature that we call ductile to brittle transition temperature. But it seems that it fails above that temperature. And the two reasons are this, in my opinion. So you can see things that you may work in the future on. Thank you very much. I have given some, I think I stuck to my time, right? I have given some things to read here. I think the slides will be posted on the webpage. The early experimental evidence for cleavage, the first papers, starting with the Berryman. Mind you, Berryman is not a person. I don't think everybody knows. Berryman is a group of people in France. So that's not just one person there. And then it's just selection of papers. There are a lot of papers on cleavage fracture that you'll find, particularly if you look at number 9, which is a review, you'll find out references to almost everything that has been published in cleavage fracture. Thank you again.